Start streaming. For those of you that may have missed it when they first came in, your headbands are out if you handed them in before. Make sure you pick them up before you go. Whenever I have headbands, I'm starting with the person picking them up. I should try to pick them up outside last time. Here. Francois, there we go. Brooklyn, there. Dylan, Simon, Kaylee, Denzi, Sabina, Heather, not here today, Valerie, and then Jaden, and then Jonas, not here, Thomas, and then Davis, Chet there, Veer there, and Lillian there. And it's recording. And once you're done, put your laptop away and pull out your notes. Studio. Okay, we started this last day. Did I give you enough time to like write this down or anything? Or are you still doing that? You should draw the table as accurately as I drew the table. Just so you know it's a periodic table. As well, you can get out your periodic tables and make a note on them as to the direction of these trends. But it should also be roughly in your notes as well, because if you lose your periodic table, then you've lost all that information. And in my experience, periodic tables sometimes get lost. We're discussing metallic character. So metallic character is all the properties of metals: malleable, conductive, ductile, conducts electricity, conducts heat, that sort of thing. And given the trend we did last day, you are the least metallic over to the right and up to the top. So what would be the most metallic element? Jaden. What would be the most metallic element based on that trend? Or here, I'll put the trend back up. Francium. Francium's a good one. Right over here, furthest down, furthest left, most metallic. Now then follow up. Veer, what would be the least metallic?
Is it neon
Neon?
or helium?
Helium would work better. Now I have a follow-up question because you got to hear the previous example. What would be the least metallic element that actually reacts with something? Neon is a noble gas, doesn't react with anything.
Fluorine.
Louder?
Fluorine.
Fluorine. So reaction between fluorine and francium would be epic. The most metallic with the least metallic. They would come together. Francium desperately wants to give up its electron, and it's so far from the nucleus, it's easy to do. Fluorine, everything's quite close to the nucleus. It's hanging onto its electron tightly, and it wants to grab another one. So to go back to here, we have the least metallic. Oops, I moved that. And then the most metallic. This will come together a little bit more when we do metallic character. Malleable has a lot in common with melting point. And so the more malleable, the lower the melting point, the more likely it is to be a liquid, for example. And that certainly holds out as, if you look on that periodic table, francium and the element right above it, cesium, are liquids at room temperature. The melting point goes down as we go over here, which would be the next trend. Good. Anyone still ready? Excellent. Melting point. Oh, hold it. You were still ready. Put up your hand or something. Go. No, go. No, we'll wait. Yeah. While you're doing that, I could have a class discussion because Lillian has decided that observations can never be wrong, and so that would be a good one. How many of you would also say that observations can never be wrong? How come? It's just what you see. So your subjective experience can't ever be incorrect. Yeah, same thing with Lillian said. How many of you think your observations can be wrong? And some of you didn't put up your hands at all. So start there. I think yours was first. Yeah, Kaylee. How would you know, though? Pardon? You could be colorblind. But wouldn't it still be true for you? But red doesn't actually exist, does it? Anyway. Like I'm colorblind and I say it's gray. It is actually gray. No. Other people just make up colors to put on top of it consistently. Oh, you're interrupting now. Put up your hand. Simon? But is their observation wrong? Or just different? Yeah? Like what? Say, give me an example. Right. But what's wrong with that? Yeah. Yeah, you could say it bubbles is an objective observation. but it's a gas may not be, depending on the cause of the bubbles, and the reasons for you to see that. So we do have some people who think you cannot be wrong, a smaller number with an observation, and some people who think that you can be wrong. Observations do have two halves. You have the subjective experience. How dare you say that my colorblind description is incorrect? That's just prejudice against colorblind people. But on the other hand, if you check with other people, it can be wrong. So this came up. I don't agree with the Hebden answer, and I don't want to correct that. You don't have to correct things. If you think your answer is still right, just write a little defense. It doesn't have to be long. I still think this is right. I am good with that. In fact, I would really enjoy that if you did that in your textbook. Now, you were contributing. This whole thing was so that you had time to catch up. Stop. Yeah. Are you good now? Okay. That's a little review of subjective and objective content. Hold it. Actually done? Then you're talking to Simon again. Oh. Yeah, you got a lot of catch up to do. Yeah. I find it useful not to miss classes. Just as a hint. Yeah. Yeah. Don't get sick, number one. And number two, I just have 4 letters. 4 letters will fix your time here. Yoga. It'll help. What? You know what? I think yoga would help that. They have lots of breathing exercises. Look, yoga is good exercise, and it would help your mental health, and there's no away games. I'm not saying the last point is the main reason. We should have a yoga day. Who's the yoga teacher? No, seriously, who's the yoga teacher? Later on the year, I should invite her, and we should have a yoga day. Okay. No, like we should have a class. Yeah. Okay. Melting points increase across the periodic table until the staircase line. And then it decreases. And as you're writing this down, I'm going to really annoy you in a second because I'm going to take it away. So be prepared. And boom, it's gone. The reason I'm going to take it away is I'm going to explain this with another trend you already know called reactivity. We have a staircase line here. Over here, what was the reactivity trend? You can't even read that. Never mind. Did it get more reactive or less reactive as you went down? Yes, Dylan. More, what? More. So if you go down, you got more. But what about this side? Ignore those. What about this side? Yes? Which is, as you go up, more. And that switches at the staircase line, because that's when it switches from a metal to a non-metal, from things that are trying to give up their electrons to things that are trying to take electrons. And so the reactivity switches for the same reasons. When you're trying to give up electrons, then you become more reactive the easier it is to give them away. But if you're trying to gain them, then if it's really easy to give them up, you don't gain very many. So the reactivity trend switches. This is the same for melting point. Down here, francium is a liquid. Over here, oxygen and fluorine are gases. The solids are all down here. Whereas here, the solids are and the highest melting points are all up there. Yes. What about the what? A difference between what? Oh, you're asking what happens at the edges? Yeah. Oh, yeah. No, they're semi-metals. I don't play around with them. These trends all go weird. Because here's when the trend switches. And so, yeah, what I'm talking about is sort of a general trend. And what we're not going to talk about is like, even though it becomes more as you go down. Why is tungsten a little bit more reactive than molybdenum? Or, sorry, the other way around. Why is molybdenum more reactive than tungsten, even though that's opposite of the trend? And the reason for that is that we're in chemistry 11, and we're not going to discuss that. It's quantum. It's a lot of quantum. Oh, some people were asking when your next test is. As soon as you know quantum. Because we're going to go into bonding, and then we'll do quantum, and then you'll have your test. Because we're doing a lot of review of chemistry 10 with new stuff. We did calculation of isotopes. We're doing trends. Then once we do quantum, we got enough new stuff in there to make a nice little test. So that'll be soon. Decreases. Yeah, I can check. Let's go. There you go. Booyah. So within the melting point of metals, melting points decrease down a family. Within nonmetals, melting points increase down a family. You do not have to write down this entire next graph. It's obviously being live streamed, so you can go and look at it if you'd like. I'm going to scroll down, yell, or in some way stop me if I scroll down too far.
Yeah.
Well, like the first line?
Yeah.
Okay, I'm going too fast. Oh, that's a lie. My observation was that I had it for 5 seconds. And because my observations are always true, this goes right back to mint chocolate ice cream being the worst type of chocolate ice cream. What? Oh, peanut butter chocolate ice cream. One, it tastes the best, and two, it's extra cool because it also can kill people. Peanut butter. Yeah. I haven't had an espresso like the drink. Oh, ice cream. I like coffee ice creams. Yeah. Yeah. Chocolate espresso peanut butter ice cream would be fairly good. No, mint chocolate ice cream is just terrible. It's not even ice cream. No. Did you disagree with that? You can't. You can't disagree because that's my observation and it's 100% true. No, it's subjective truth. I honestly don't like it. No. Like, if you ask other people, they'll tell you I don't like it. So it's objective. And I define all ice cream as good or bad based on how much I like it. So that's an external source. You just have to consult me. I'm scrolling down now. Is the first line okay? Oh, pistachio I've had is pretty good. But the weirdest one, if you go, you know the little farm place just up the road, Sweet Meadows? If you haven't been there and you're a new student, when they have ice cream, it's fantastic. They make it right there. They did sweet potato ice cream. And that's amazing. And I don't even like sweet potatoes. Yeah. They're not good. They're like if you took a potato and then you just said, how can I make this slightly worse? Hold it. I also forget. Which one's the really yellow one? Sweet potatoes or yams? Oh, okay, no, it's yams that are terrible. Sweet potatoes are okay. They're a second. Yeah. Yeah. Well, when you can't really tell them apart, are they actually all that good? No. I'm scrolling down again. Yes? This table? No. I'm going to use it to illustrate a point. And I'm almost far enough down that I can. What was that beep? Lillian, why is your laptop out? You have two devices out at the same time. Well, you have to be able to write. Yeah. Okay. So this is the trend of actual melting points. Here it is in degrees. So, lithium melts quite quickly. So just so you know, these are up by thousands. So here's the trend for the first metals across the periodic table: lithium, beryllium, boron, and carbon. Whoa. And then here's the trend for the non-metals. So we're going this way. I'm exaggerating. And then we're going this way. So the trend is increasing across the metals, then decrease. Now, it's not as obvious, the decrease, but you see the same trend here: increase, and then decrease. And again, I'm looking at the only trend. So if you come back with, well, this little one went up first and then down. No, it didn't. It's just downwards. Yes. Oh, you mean here in the transition metals? Whoops. Here? This? Yeah, we don't discuss those. Well, it doesn't take long asking questions in science before you reach the edge where we honestly don't know. If you've ever had a question, answer section with a toddler, and they're like, why? And they're like, well, why? And then very quickly you're like, well, that's the limits of human knowledge. Yes? Yeah. Well, religion would be a subset of biology, which is biochemistry, which would be chemistry. But also the purpose of religion is to worship chemistry. So, two-factor approach there. Yes? They're just spontaneous. Just spontaneous. Okay, next section. You do not have to write all of this. We will be writing some of this, but this is to remind you of the section we did in your book. You filled out that sheet, and you had like 1, 2, 1, 2, 8, the electronic structure. That ringing a bell? Yes. Good. So now we're talking about nuclear attraction and electron repulsion. And I'm going to have this here for reference because keeping the electronic structure of these atoms in mind is important for understanding, especially things like atomic size, and will allow us to explain things like the reactivity, long distance relationships, and all of that. We'll do the notes on it after. Well, let's just get this down, and then I'm going to show it to you. Yeah, the words underneath, like all the words are important because they're my words. What's happening to your laptop? Oh, sorry, never mind. That's what my laptop does when it overheats. Well, the first thing I'm going to do is go down a family. So, oh, people are still. You're not writing verbatim, though, right? No. Actually, I haven't even explained it yet. But I'm going to get Veer as a volunteer in just a second. It's okay. Just finish up and then come on up. Over here, it's a little bit louder. And you know, as a proton, we're the most attractive things. Everybody else are electrons. Right? Well, I randomly selected these two rows. So I'm going to work backwards there, work backwards here, and then we might actually come around. About right there, I think, beside the killing. Because we want the distances to be relative. So, proton, electron, positives and negatives attract. And so, now I don't want you to actually buzz around like a real electron, so we'll just use this as red. So, we have, first of all, what element is this? There's a hydrogen. Okay, so we have one layer of attraction. But we're going to add some more attraction. So, we need lithium. So 2 more protons. Yep, form a group. Now, protons are best buds, always, because they have a strong nuclear force. So we don't have to worry about that repulsion. Like, they're together. They're tight. Now, obviously, far more attractive. So you take like a step forward because there's even more attraction. But if I added 2 more protons, what do I need to add? Another electron. So can you stand up and go where you think the next electron should go? Pardon? Yeah, basically, yeah. So we got to, but are we done with the electrons? No. Where do you think you should go? Well, you wouldn't be with them. You'd have to be behind them because you're in now a different shell. So even though there's more protons, and it pulls them in a little bit, stay right in the middle there. Because now, what charge are the electrons? Pardon? Negative. What do negatives and negatives do? They don't what? They repel. So, although you're still, as much as you can be, you're attracted to them. But that's the greatest nucleus ever. But you're giving hate cleanses. Like, this is our. So, your full attraction can't be realized because they're in the way. Does that make sense? So what happens is you go down a family. I won't, like if I go down again, I have to add a bunch more protons and a whole other level of 7 more students. Probably won't get there. But what will happen to the size of the atom as we go down a family? This? You're right. Yeah. Yeah. We'll have, you could say, I mean, we have another orbital, another extra electron cloud, because the inner ones are actually repelling the other outer ones. So, I mean, she can't get as close as she would like to the really attractive nucleus. However, what about if we go across the periodic table, not down family? So I'm just going to add 1 more proton. Now, 4 protons. More attractive to the electrons or less attractive? More. Like, just look at what we've added. so attractive. So, but if we add a proton, what do we need to add? Electron. David's been like volunteering every 3 seconds. So, same orbital or further orbital? Same. But are you two interfering with each other? Yeah, like these are interfering. But are you two? No. So in the same orbital, they're not interfering. So would you get closer or farther apart? Closer. So we're going to take like a half step forward. Yeah. Protons obviously don't change, but now we can add another proton. Yeah, sorry. There. So, but if we add a proton, we have to add an electron. Come.
Check.
Yeah. Even you got to bunch up more nucleus close together, even more attractive. Now what happens? I like the whole thing. I mean, it's not COVID friendly, but you're together in the same orbital. What will happen now?
We get closer.
We get closer. So what's happening to the size of the atom as we go across?
Shrinking.
It's going to shrink. So even though we're adding more protons and adding more electrons, you would think it would get thinner. But by adding more protons and electrons, you're actually adding more force to squeeze them together. So now we could just increase it by another 2. So we've got right here 2 protons. We just jump ahead. No, you can't do that. You can't fundamentally change your mass. Okay? And then the other 2 go where you think you belong. Is this orbital even close to being full yet? No. 1, 2, 3, 4, 5. So what will happen now? We added like 2 more protons. Yeah, we're all just going to get smaller. So as you go across the periodic table, it's getting smaller and smaller and smaller, even though you're adding more and more stuff. And I do this in this kind of silly fashion to just really emphasize, even though you're adding more stuff, it's getting smaller because what you're really doing is increasing the attraction.
So the larger atoms are actually smaller in size.
The larger atoms are on the left of the periodic table because there are larger. If we go down a level, what happens to the size?
Oh, I mean like the ones with the more
Volume. Yeah, have less protons and neutrons in a row, like in a row across. The larger ones are over way on the left. Yeah. If I wanted to make this atom bigger, how many more protons would I have to add? No.
You have to move down.
I mean, but I want to make it much bigger. How many more? How many we got there?
4. You've done 4.
We had 4 because we're 5. I would add 3 more to fill up the shell, and then 1 more person to put them on the other side, and then we'd have 2 of these. Now, in here, what these are doing is they're acting as a shield against the full attractive force of the nucleus. Because when you look over, you just can't take in all that attractiveness. They're in the way. They're shielding. Okay, excellent. You can have a seat. Give yourselves a hand. There wasn't very much of a hand. Yeah.
Upside down.
It's not upside down. Come, look. World. Everything's written.
Why is it upside down?
It's not upside down. No, it's the world. Because how you draw the world is arbitrary. Why do we put the north on top? No.
Is this the scale?
Yeah. Well, roughly as much as a square mass can be.
That actually makes me not like, because you know what this Greenland is bigger than South America.
Oh yeah, this is not size correct.
Yeah, everybody thinks Greenland is bigger than South America.
Yeah. That's not. Because which way you make north is arbitrary. Like we've said this is north, but which way you draw the map is arbitrary. Right? That makes sense. Yeah.
Because the world is upwards.
Yeah. The world is upwards? What?
Well,
You mean the disk?
Not the disk, the globe.
Yes. Anyway, have a seat. We got to finish these notes. Enough of the maps. Okay. So down a family, I'm going to ask you to draw this here. So everybody's down here. I am going to ask you to draw this one because I'm going to draw on the forces that are applying. Applying. That sounded like an odd way to phrase that. But the forces that are present. Now, one thing I don't discuss is why do all the protons in the nucleus not take off? And yeah, I just don't discuss that. It's called nuclear force. Stop asking questions. And so there is an attraction from this very positive nucleus Yes. It's empty nothingness. Absolutely. Well, you've heard, like, you've read things about black holes and how much matter gets compressed. Like, if you compressed yourself so that you didn't have any atomic space in you, it was just pure like protons and neutrons, you would easily fit into a thimble. Like, you're tiny in terms of actual mass. Also, I mean, weirdly, like, protons and neutrons don't actually have mass. Nothing has mass. It's an effect that occurs when some particles move in a gravitational field. They experience like drag, and that's what mass is. But it's not actually a property, because if you take the things that make up protons away, they don't have mass. Anyway, that's a topic for a different day. Whereas the forces between the electrons have a negative and negative repulsion. So the nucleus is like the really, really popular person, and these are their fans who don't like each other. These are the Star Wars fans, who are the original fans who don't like the prequels or the sequels. They kind of repel those who like the prequels, and they repel those who like the sequels. And then way out here, you'll find ones that just like everything.
I don't get Rogue One.
What? That was one of the best ones.
Oh, the Disney Star Wars ones aren't good except for like
Mandalorian and Rogue One.
Rogue One's alright.
Rogue One was good. That's the only one that really had a story. So there's a magic word in here for that effect we just acted out, and you should know this magic word. It's called the shielding effect. That is why atoms get bigger. Because inner electrons shield or repel outer electrons, puffing it out. So the attraction of the nucleus to the electron weakens. I think I should have another word here. Weakens as you go down a family. So we have a tension of forces. They're all attracted to the nucleus, but they're repelling each other into these layers. Only so many fit in a layer. And if you ask me why only a certain number fit in the layer, I'm going to say quantum. So this is especially as you go down the family, you get the shielding effect and your atoms are getting bigger. Now if we go across, what we just acted out, I'm going to scroll to the next page. But yes, good. Anybody else? No, everybody else is good. I do want you to draw these, but I am also going to draw them. You don't have to draw them way up there. That's just a reference for me. So I have 3 protons in a nucleus. How many electrons in the first shell? 2. And 1, we have 1 left over. Now when you draw it again, oh, hold it. I want to make this really obvious, so let's do that. Yeah. When I draw it again, with 4 protons, I'm going to keep those 2 electrons. So the shielding effect in this case is going to be consistent. But when I put in the extra electron, I'm not choosing to put 2 electrons. I'm going to put them separated because I want to emphasize that they're not interfering with each other. They are in, you can think of them like in separate locations. And so for here, we have a 3 proton attraction. And here we have a 4 proton attraction. It is literally smaller, even though it has more stuff. And so that is attracted to there, and that is attracted to there. And then when we have the 5 proton attraction, we have the same shielding effect, 2 electrons. And you get a 5 proton attraction. What electrons are these outermost electrons called? Valence. Sorry? Valence. Now I can ignore this. Now, unlike the shielding effect, which had a fancy term, there is no fancy term for this. It's just increasing electrostatic attraction. Have you heard the word electrostatic before? Hands up if you have not heard the word electrostatic. You have, or what it means? I will write it below here. There's a last little thing here, but it's a really fancy word for something you already know. When someone says electrostatic attraction, yeah, that does use electrostatic attraction, And electrostatic attraction is just positive and negatives attract. That's the fancy term for positive and negatives attract. It's useful to know, like if you get invited to a party. Well, because you fancy terms are great pickup lines. Like you walk up to someone, they're clearly out of your league. You know, they're either goth and you're not, or vice versa. Like it's just, but I feel that there's a strong electrostatic attraction between us. Pardon? No, all the parties I've gone to, that's worked. I don't actually go to any parties. I'm just sort of imagining what parties are like. Mr. Sullivan just invites the cool teachers. I hold my own parties. Party of one. Actually, to be honest, when we used to have them, because we didn't during COVID, but they would have like an end of term dinner for all the teachers. I and Mr. Snow would show up and we would play Civilization 6 with each other while everybody else is like pretending to gamble or something. Pardon? No, I like 6 quite a bit. 2 was the best. But I liked 6 in its rebalance. But 5 was fair. And then Mr. Snow didn't come next time, so I just brought my Switch and played Breath of the Wild. Yes. Electrostatic attraction is positives and negatives attract. So it is the word for that they attract. And electrostatic repulsion is similar charges repel. So if you have positive and negative, so electrostatic is just the word for that phenomenon. And I don't. Do they still teach like grade 6, 7, like electrostatics? Do you like at some point did you like get amber and a piece of wool and rub it on things and attract stuff? Oh, that used to be in grade 10, but they moved it up. I thought maybe they put it somewhere else. Like the reason a balloon sticks to a wall. Oh, when you rub something that's an insulator, you can actually rub electrons onto it or off of it. So let's say you rubbed electrons onto a balloon, and that balloon approaches the wall. The wall has an equal number of positive and negative. Can the positive move? Can the negative move? Yeah, just electrons. So the negative all move out of the way. They go over here. And then as this balloon comes closer, you have an area of positive charge, negative charge, and an area of positive charge, so the balloon sticks. So a charged balloon will stick to a neutral wall because its mere negativeness moves all the other negatives away, and now you have a positive negative surface. That's how static electricity works. It only works on insulators, because if this was a conductive thing like a metal, metals don't do static electricity because the electrons would move back too quickly. Like they can just ground themselves really easily. Whereas if you have an insulator, they only move little bits and they can't move around the whole object. And so that's why things like wool and amber and various plastics in your shoes, when you rub them along carpet, you build up some electricity. Then you go and touch your sibling and then they jump because you just shocked them. You built up a charge. That's how clouds work. They rub literally in the atmosphere, they build up and charge, and you get lightning as the charge tries to ground itself. Lightning? Yeah, lightning not as much here. It does on occasion, but Alberta was amazing. When I was there, they had a number of lightning storms. Increasing nuclear charge results in the attraction of the nucleus to the electrons, strengthening across a period. So this is why they're getting more and more attracted. This would explain why magnesium is less reactive than sodium. We gave it an extra electron, but we also gave it another proton. Now those two electrons are experiencing a greater force. Magnesium has to give up 2 electrons in order to be stable, but it's got an extra proton holding on. Sodium will give it up really quickly. It's just got that one extra proton there. Well, it's 11 protons, and that one extra electron can just go. Add another proton, and it's holding on to its electrons a little tighter, a little harder to let it go. Magnesium is less reactive. Now we'll get to aluminum, which is pretty stable as a metal. Magnesium, as you saw, will burn at high temperatures. It does slowly decay away, oxidizes. Aluminum is pretty stable. Its electrons and protons are holding on so tightly that it doesn't readily become a +3 ion. It doesn't give it up all that easily. It can, and you can convince it to with a variety of reactions, but it's also perfectly happy being aluminum, the metal, and neutral. And so these explanations, you can now start explaining these trends in the reactivity series. I have a handout. What time is it? 5 minutes. And I finished the thing that I wanted to finish. And I'm not going to do that. So I think once you have this down, and if you're good, the explanations made sense, you're good to go.